welcome back. So today I'm going to be presenting my ISMB ECCB presentation that I did in Lyon. So if you couldn't be in Lyon, or if you just like that presentation so much that you want to see it again and again, I'm recording it again for YouTube. So this is a proceedings presentation. So there's a manuscript associated with it. All of the links are below in the description, but otherwise I'm going to go ahead and get started. So this is mostly work done by Xiaojun Pan, who's a PhD student that's being co-supervised by myself and Xingming Zhao. So I get to present it, but this is mostly Xiaojun's work. So all of these links will be below as well, including the link to all of the slides. So this is exactly the presentation I presented in Lyon. It's exactly the presentation I'm presenting here today. So without further ado, let's get started. And we are talking about metagenomics. So what that means is that we have these genomes in the real world that are bacterial genomes, and they are very nice. They are circular, complete, and as we know, and this is the microbiome, bacteria do not live by themselves. So we're going to have here maybe some of this magenta species and some green species and some of the purple ones. And some of them will just be more abundant than others. We'll have multiple copies of the green one, many more than the yellow ones. And in a typical metagenome, we'll have many more these, maybe hundreds of species. But when we actually sample the metagenome, we get these short reads, or even the long reads, they are much shorter than the original genomes that they come from. And here I'm showing you, and I'll be showing these colors to say that we have some green magenta reads and some purple ones, but in fact then this is the whole issue, we don't know which genome each read comes from, right? So the first thing we can do, and we do this, is we can assemble them. So that means we group the reads into larger blocks, so-called contigs, and we're going here to assume that the contigs, they represent a single chunk of genome from the original genome, and that this effect that I've shown here with a magenta green contig, which would say a chimera, we're going to ignore that, because in fact in Xingming Zhao and myself with another student, we've shown that this is actually quite rare that we have these chimeric contigs. So for the rest of the presentation and in this work, we're going to assume that they are so rare that we can ignore the problem. Where our talk comes in is the binning problem, which is, okay, now that we have these contigs, can we group them so that to the best approximation, each group, a so-called bin, comes from a single original genome. Right? And here this would be quite nice. We would have grouped purple and magenta and green, and here there would also be an unbinned section. And so we've actually missed a little bit of the purple, a little bit more of the green, and we couldn't group the yellow ones at all. But here maybe we'd still get 3 good bins. So if you're coming at this with a more traditional bioinformatics or machine learning background, you might be thinking to yourself, oh, this is just a traditional clustering problem. And you'd mostly be right. I mean, we have a set of contigs, a set of objects, and we want to group them into clusters. And we typically use features for this. So there's 2 groups of features. So one is abundance. So how, if we have more genomes from a certain species, we are also going to have more contigs from those genomes. And this actually works very well, especially if you have multiple samples, because things that go up and down together probably belong to the same genome. And the other feature that we use is k-mer composition, because genomes have a characteristic k-mer composition that we can exploit in this setting. So k-mer is we simply take our DNA sequence, and we in SemiBin, and this goes back about 10 years, we use k equals 4, so formers, and we just count how often each of these formers appears, and that's our k-mer signature. Completely different way of doing this, which we can also do, is to classify contigs. So if you can do clustering, you can do classification, and then we just use the standard methods in bioinformatics, often based on sequence identity, or to infer homology, and to say that yes, look, this contig comes from this species, that one from that one, etc. And actually, if this worked well, we wouldn't need to do binning, right? But there's 2 issues with this. So number one, our sample might contain species that are completely unknown. So maybe the green species is not even in our database, so it's impossible for the classifier to output a label that it doesn't even know it's a possibility. The second one is the magenta, here where the classifier does know about magenta, but strains, bacterial strains, they have a lot of variation, and so it might be possible that we have this magenta strain or magenta contig that is just so different from the magentas that are in the database that the classifier cannot assign it. So depends obviously on which environment you're studying, but often the majority of your contigs will not be classified, at least not at the species level. Sometimes you might say, oh, it looks like this phylum or this class, but the real species level classification is normally not possible, or it's only possible for a fraction of the contigs. And so SemiBin2 approach, and and here in this presentation I'm going to present first the main ideas of SemiBin2, and because this makes it clearer why we needed to improve what were the weak points and how we've tackled them with SemiBin2. But the original idea of SemiBin2 was to then use semi-supervised learning. So we have these contigs, as I said, and we are going to be doing two things to them. So the first one is we assume that they are pure. So if we break up a contig, and we do this artificially, we can have these two smaller contigs, artificial, that are that we say they must be linked because they came from the same original assembled block, so they must come from the same genome. They must be linked. Alternatively, if we can classify two contigs confidently into two separate species, then we know that they cannot be linked. So we say that we have these cannot links and these must links. And then we calculate the features, so this was as before, and then we learn this neural network embedding that tries to, as best as possible, reproduce the supervised information, but then we can apply it to all of the dataset, including the ones for which there is no classification, and then perform some clustering in that embedded space. So we've used the supervised information to learn an embedding, and then with that embedding we do the clustering, the unsupervised clustering. So this is a form of contrastive learning. So just to put it a little bit more formal, so we have our input X, and so here if we have former, that's 136 dimensions because we count a k-mer and its reverse complement as a single object, and then we want to output X prime, so we want to learn a function f from X to X prime such that the must-link contigs are as close as possible and the cannot-link contigs are as far away as possible. So we defined the loss function in two steps. So there's a positive loss, so the must-link loss, which is the distance between must-link points, that's a loss. And then in the other direction, here we just need to be a bit careful so that things don't explode, but 1 minus the distance for the cannot linked one. So the cannot links should be at distance 1, and the must links should be at distance 0, as close as possible to these as possible. So the total loss is the sum of the two, and then f, the function, is a simple multi-lane network. And this is all very standard if you have this machine learning background, and we also didn't come up with this idea, so there's a link there to the original paper, but we are applying it to this setting here. All right, let's jump to the conclusion. Does it work? Yes, it does, and so we used, obviously otherwise I wouldn't be presenting it. So we used Kami data, so this is simulated data set, and we have that in the manuscript, but here I'm going to be showing you results on real data. And we're counting the number of high quality mags produced as our main objective. And so since we don't actually know the ground truth, we use these two tools, so checkm and junk, to predict, to give us an estimate of the quality. And we've used 4 data sets, about 100 samples each, so a human gut, a non-human host associated, and then marine and soil samples as environmental. And then the results look like this. And so this is the number of these high quality bins for a couple of different alternatives that we looked at. And our bars are the green bars. And so throughout, so you can see a green bar is larger. So it means we have more high quality mags. And here we have either when we use a single sample or when we use multiple samples. So multiple samples is best but in both settings, green bar is higher. So we do better when we have multiple samples, and we can see that so here each dot is a single of these samples. So there's here 82 of these dots, and in each sample we're always getting, or almost always getting, more bins per sample. So, and this is obviously a statistically significant difference. Okay, so great, we're doing better. So are we doing better because of all of this semi-supervised embedding, or are we just doing better because we have really good clustering method? Maybe we just got really lucky with the clustering method, or maybe using the supervised information is good, but we're just going about it in a very roundabout way because we learned this embedding, instead of maybe we should just say, okay, if these two things shouldn't be in the same cluster, instead of learning an embedding that represents that, let's just force the clustering method to not put them in the same clustering, right? And so we did these so-called ablation studies where we've taken the full pipeline, and then we've taken out the semi-supervised step, or just use the other the supervised information directly. And again, green is the full pipeline and green bar is higher. So it does seem to matter that we have more, that the embedding does seem to be capturing information, right? So because we're using supervision, one of the fears was as well that, because remember we had there's these two different issues. So one is with the supervision is that we don't know anything about the green, and the other one is that maybe magenta has variations that we don't know about. And this would already be excellent if we could do this. So this would be great if this would already be a big step, but maybe we're just doing a lot better at recovering these new magenta strains, but we're not really learning about new species. But we do learn more species than other methods, and actually across different taxonomic levels. So here, so green bar is the species and genera that are learned only by our methods, and you can see that we regularly do better. So problem was then, so here with this approach is that we're learning a new model, and this takes a lot of computation, and in particular generating the data for training was taking a lot of time. So we were using MM62, which is really, really excellent. It really gives us really great results, but it comes at a cost, and it comes at a cost in computation. And it comes at a cost in memory requirements as well. So here, just for example, this is single sample mode, average, but it's an average across samples, and you can see that especially here, generating the cannot link features, it was requiring a lot of memory. And this was taking a lot of time. And the actual binning is very fast. Actual binning is very cheap. So the first idea was, okay, so we have a model, but maybe we don't need to learn a model for every single sample. Maybe if we have 100 samples in our data set, maybe we can learn a model from one sample and then apply it, or maybe learn it from a handful of samples and then apply it, but pay this computational cost a single time. And that really worked very well. So you can see that this is the number of samples used for training, and so here this light green is learning a single model every time instead of reusing the model. So would be learning about 100 models for each data set. And actually, when we learn a model from multiple samples, we do better than learning a model each time. So this, just to be clear, so for example, this would mean that for our human gut data set, we take 10 samples out of the full 82, and we learn a single model from those 10 samples, and then we apply it to all 82 samples. So we're still paying the computational cost, but we're paying it a single time, and so this could scale very well. And in fact, we then went a step further, and we thought, okay, can we then learn a single model for one time for human gut, and then just apply it to all human gut data sets going forward? And that really does work quite well. Even we tried transferring between two German human gut data sets, thinking that it should be very similar populations, and between a German and a non-westernized African human gut data sets, which still the same biome, but should be more different populations, and they still worked really well even across geographies. In fact, here sometimes the model from a different data set works even better. So in the case, actually, if you look at it very carefully, you can see the model learned on the African samples actually outperforms the other models. And so we've done this. We've now done this for 10 habitats, and then Florian provided an 11th, the chicken Sikkim habitat. So this is all pre-available for download in the tool. So this is where we were about a year ago, which is that SemiBin1 was really good results, but it's slow. However, for single sample binning, we can reuse models. However, this didn't work for multi-sample binning because, and I'm simplifying a little bit here, but for semi-sample binning, for multi-sample binning, if you have 17 samples, we need a model for 17 samples, and then we would need a model for 18 samples and a model for 19 samples. So it's not so trivial for us to provide pre-trained models for all of those contingencies. And the second, all those contingencies. So we thought, could we do a little bit better than we were doing? And so in the SemiBin1, must links were self-supervised, in the sense that we were just exploiting the structure of the problem, where cannot links were from a reference taxonomy, and this was one of the very computationally heavy steps. So, maybe the easiest is to just completely bypass this reference taxonomy and just generate cannot links randomly. Just take two. If you take two contexts completely at random, they should not come from the same genome unless you're very unlucky. So this is really much faster, and because random sampling is much faster than MM62, and also maybe less obvious, it has no database biases. So one of the problems with taxonomic classification is that our databases are very biased. So there's some species that are very well studied, and then there's some species that frankly we don't have a lot of references for. So when we annotate the sample, we are not annotating a uniformly randomly sampled dataset. We're annotating a very biased dataset. On the other hand, obviously, sometimes we get unlucky. We might pick two contexts that actually do come from the same gene. So it's not really clear a priori which one of these two is going to perform better. So, we need to actually look at data. And so the first thing in simulated data, so here again, so green is our method, SemiBin2 now in green. And you can see that basically they're very hard to distinguish the two curves. If anything, green is slightly above. And then when we looked in real data, so these are the same data sets that I showed before, you can see again, green bar is higher, a slight advantage to using this self-supervised learning. So self-supervised learning, paid off, first of all, because it is much faster. So that was one of the original motivations. And also it does perform better. So this was great. And then in parallel, we were seeing that long reads are becoming more and more important. We're also actually using them in the lab in other projects that we have. And we've seen also in public data sets that the number of publicly available long read metagenomes has really been growing. And you could always use SemiBin. You run it and it would give you some results. And in fact, you can do this with almost all of the other tools. You can run it but we had not really tested. And a lot of the optimization and the parameter choices had been done in the context of short reads, so we weren't sure if this was going to work very well. And the biggest difference between long reads and short reads is that long reads are longer. And this sounds very basic, but it does mean that your statistics are going to be very, very different. So here's a triplet of samples and sequenced with a traditional Illumina and then two high long read technologies. And you can see that, if you have, so these are the contigs, so this is not the original reads that you get, but after assembly. So the contigs from Illumina are, about 2,000 base pairs, and the contigs from from the other technologies are hundreds of thousands of base pairs. And with Illumina you have hundreds of thousands of contigs, and with the other technologies you have thousands of contigs. So a lot of our intuitions and a lot of our method development really was not targeted towards this. So for example, just as an example, one of the steps, we create a sparse graph so that each contig is linked to its most similar contigs, and we had set that at 200 neighbors, thinking that would be very sparse. And in fact, if you have 200,000 contigs, it's only connected to 1 in 1,000 possible links. Whereas if you have 2,000 contigs, then it's a much denser. So a lot of and also this is much larger. It's still smaller than a full genome, but it means that your bins are some of them are going to be very, very small. You might have, if this is the average, so you might have some of them that are half a million base pairs, and so you will have bins that are maybe 4 or 5 contigs and not more. In fact, if you're very lucky, sometimes you get pure bins, so you get a single contig that's your whole genome, or 2 or 3. So what we did is we then used a different method for the clustering. So the first half of the pipeline, the whole self-supervised learning that I've been talking about so far, that stays the same. And then for short reads, we use the same approach as before. And for long reads, we now use this dbscan based method, and dbscan can give you very small bins, very small clusters. Again, does it work? We are again looking at the results in real data sets, and I'm also going to caution that here we are comparing to some of the alternative methods that were not designed for long reads. So if maybe it's a little bit unfair to do this comparison, I'll acknowledge that, but it is sort of a growing field, and people were using these for long reads because I'm not faulting anyone here. There just isn't that much out there. Again, we're using checkm, although we've switched to using checkm2 here because checkm2 came out, and it also avoids a little bit of a circularity issue, because especially for the long read approach, we heavily use these single copy genes to guide our clustering, and checkm1 also used some of the same single copy genes. So there was a bit of a circularity problem there, but with checkm2 it's a completely different approach. It's actually very nice, and we avoid this. But I can tell you that the results actually don't change if we use with either version of the tool. Okay, so I'll leave you with one final anecdote. I think this didn't even make the paper. This is one of these technical details that I actually think is kind of cool, and that is that bad ORF finding is better than good ORF finding. And here, so Vapnik was one of these giants in machine learning, especially more theoretical approaches, more theoretical investigations. And he said, do not solve as an intermediate step a more general or harder problem than the one you are actually trying to solve. So as I said, we use single copy genes, and the way we were doing this, we were doing 2 steps. We were using Prodigal, and then we were feeding to predict genes, and then our open reading frames, and then we were feeding them to Hammer to do this HMM. And the majority of the genes are not these single copy genes, right? By definition, the single copy genes are we're using 107, and so it's only a small subset of all of the genes. And Prodigal is really, really good, but again, it's slow, because actually finding genes is a hard problem. It's a complicated problem. So we decided to, okay, let's do the dumbest possible way of finding genes. Just find all open reading frames. So we'll find the start, and then tack, 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 and then we see a stop. And if we see a start and a stop that are separated by at least a certain number of positions, then that's an open reading frame. Right? And this is much, much faster than Prodigal. So you can see here, and here frag gene scan is another alternative that we tested that's somehow we're in between. So this is our naive method, Prodigal, and naive is much, much faster, right? Because we're not doing all of this really, we're not applying any models to check whether these are real genes or just random open reading frame. So in the end, we have 10 times more open reading frames, and we feed all of this into the HMMs. And our HMMs take a little bit longer because they have to process a little bit more, but in total we're still significantly faster. We're still significantly faster than the prodigal clutch HMM combination. And more importantly, the results are basically identical. There really is no, and it's not even clear that in the very rare cases, and we're talking about maybe in a full metagenome, maybe 1 or 2 genes get predicted differently, which in the examples I've seen does not even affect the binning. It's not even clear that it's our method that's wrong and not prodigal. So gene finding is really, really hard actually, and prodigal does a lot, but here we just didn't need that, so we didn't need to pay all of this computational cost. So as a tool, it's available on the command line. We now have interfaces for other workflow engines, or we have documentations very, very, very complete. We have YouTube tutorials. I mean, if you've subscribed to this channel, you've maybe seen some of them, and we'll probably put some more out in the near future. And we are very committed to high quality software and maintaining it over the long term. And so we do want people to use the tool as much as possible. So even people who might not care anything about anything I've spoken up to this moment, but they just want the best results, SemiBin is still for you. So let me just in summary. So SemiBin1 was semi-supervised binning of metagenomic context, and it really got really good results. But it was a little bit slow, and it didn't work well for long read context. So with SemiBin2, we've made it much faster. In fact, it's the SemiBin, the original name comes from this semi-supervised learning. We now don't actually use it anymore, or we don't recommend it anymore, because it gets better results at a fraction of the cost, and we can now do long read as well. And now we're actually applying this extensively. So I want to again acknowledge that Xiaojun Pan was the main author and the main driving force behind this. So a lot of users have contributed a lot. Florian, I've mentioned his chicken sequence model. He's also contributed a lot of bug reports, and Berenice contributed the Galaxy wrapper, and but even people who too many to list here, who just commented on anything that's really helpful. So I want to thank them. I want to thank NSFC for funding the work, and I want to thank you. So that was my talk. So if you have any questions, please feel free to comment below. There's also links to everything related to SemiBin. We have the GitHub. We have the